Hello everyone, I'm Alexander Spiritakis from Virtual Open Systems. I work as a software engineer for virtualization issues, and in this session we will give a short introduction to virtualization concepts. Virtualization in general is a difficult term to understand for uninitiated people. Normally they are confused about what is described and what its purpose. So in order to introduce the concept, I think three main questions are important to answer to the audience. So, what is virtualization, why we need it, and how it works, and how can we make it better? So, what is virtualization? The concept started in its history around the 1960s, mainly due to have to do with mainframes, where scientists at the time were trying to divide computer resources for different applications. Since then, over the years, the term is quite overloaded with many different purposes and meanings, but mainly in computing, virtualization refers to creating a virtual something, a virtual thing, rather than an actual. Of course, this thing can vary and have many different meanings. For example, it could be to virtualize CPUs, to virtualize memory, or operating systems, even applications and peripheral devices. But the concept is mainly the same, to create a box within a box, or as most people know, to create a virtual machine inside a physical machine. Why we need virtualization is the most important question. Mainly, virtualization nowadays is used everywhere and affects everyone, even indirectly, even when most people do not understand how virtualization changes their lives. So mainly it's a tool. It's a tool to explore problems, see how they work, make results better out of them, but also a tool for many purposes and different goals. The uses of virtualization cannot be summarized in one small presentation, but some examples, major examples that are given in the industry are mainly servers, of the utmost importance, virtualization, the subject, and networking. Then testing environments, people actually use virtualization in order to create, once again, these virtual things in order to deploy them, test them, develop them further. Virtualization offers isolation and security. When you have multiple operating systems, for example, you make sure that they're isolated, they cannot communicate with each other in a malicious way. Of course, other types of use cases include legacy systems, where you want to virtualize old software or even old platforms to run your software. And of course, the cloud. Basically, virtualization offers far too many features, and it's the bare bone element for the cloud infrastructure in today's internet. So, about virtualization use cases, because that's the most important aspect that people need to understand. The use cases and how we utilize virtualization to do better things. The main example here is mostly server consolidation, where we have, in the past, we were leasing physical machines to users. So one user had one physical machine, and that's it. It was simple as that, but if the machine was idling, it would waste resources. If the user stopped leasing the machine, it would sit somewhere taking dust all over the place. So instead, virtualization is used to a huge pool of processing elements, and you lease virtual machines instead of physical machines. That way you can you can handle your whole pool of resources much more easily and efficiently. For example, this big pool of processing power can be dynamically reorganized based on the load and the users and how many virtual machines are deployed in the system. As you see in the picture here, these are the physical elements, and nowadays we have a large pool of elements which are then virtual machines are created dynamically. So, after covering the use cases, we need to speak a little bit about the examples. So let's give a couple of them in this slide. One of the major examples for virtualization is software development, multiple operating systems. So the user would boot multiple operating systems in order to be able simultaneously to feel and use different environments according to the needs of his job or even his hobbies. In that respect, a user could also develop different applications for different operating systems, and virtualization offers a way to do that in a single machine without having to invest on too many resources. Another example is legacy software, as it was already mentioned, and hardware support. Imagine gaming, for example. Gaming consoles of the 1980s or the 1990s are now long gone, and the software is not anymore maintained. So in order to feel how this software was executing at the time, we need virtualization. Virtualization to run the legacy software, but even to emulate the whole platform, for example, a gaming console or very old hardware. Another interesting example is network function virtualization. This is an ongoing process. It's the latest paradigm in virtualization, where network vendors are tied up to specific physical machines for specific network functions. For example, routing, packet scheduling, packet throttling, whatever you can imagine. But these physical machines are very expensive and lock down vendors to specific hardware manufacturers. So the new paradigm for network function virtualization is to move these functions instead of physical machines, again inside virtual machines. Of course, these are some examples for virtualization use cases, but there are actually many more, including the cloud and embedded systems. Regarding the DREAMS project, which we are involved, the virtualization use cases revolve around mixed criticality systems. When we say mixed criticality, we mainly have to consider systems where they have varying levels of criticality in software. So, for example, we have avionics use case, where one operating system is for flight control. It's of course safety critical, and another for in-flight infotainment. It's about the users, it's not so critical, but still they will be executed on the same hardware platform. So virtualization is a tool that allows this secure isolation between those two and the efficient usage of the platform with two different payloads, let's say, or even multiple ones. So the next question, of course, after the use cases and what is virtualization and why we need it, is how virtualization works. So it depends, of course, on the target platform and the system that we have to replicate. But basically, virtualization is implemented through a specific software called Hypervisor or Virtual Machine Monitor. This hypervisor is in its essence a small operating system, as it's trying to abstract resources and hide the underlying hardware from the guests' operating systems, create and manage the virtual machines, schedule the resources, and many more actually. Examples of hypervisors are VMware, either Workstation or ESX, KVM, VirtualBox, and Xen. Now, these hypervisors, of course, can be split in different types. Not all of them. One rule does not fit everything. But we have two main types of hypervisors. Type 1, which is a bare metal or native hypervisor. As we can see in the picture, the hypervisor is called bare metal because it runs directly on top of the hardware. And then on top of that, multiple guest operating systems are instantiated. Of course, the guest operating systems are not aware of the actual hardware. Only the bare metal hypervisor decides what is going on with the hardware and who talks with it and what does with it. Another type of hypervisor is a hosted hypervisor, type 2. These hypervisors are mainly started after the host operating system is booted. And again, we have the same paradigm here of virtual machine guest operating systems, but instead the hypervisor is sitting on top of the host operating system. Now, for the types of virtualization, because there are many ways to implement virtualization, how to abstract things, how to manage resources. It's a very complex process that has different types of approaches. So the approaches that we will discuss here are emulation, paravirtualization, and hardware-assisted virtualization. Depending on the use case, other approaches are better. Of course, all of them has their advantages and disadvantages, but it finally depends on the system and the use case itself. Different approaches offer speed, others ease of use, and some of them hardware dependencies or not. So, examples for types of virtualization, listing them as we did previously, starting from emulation, which is trying to replicate the exact hardware behavior entirely in software. Of course, this is very costly. Imagine, for example, a peripheral device, a real-time clock, where the host actually keeps the time, but you model a device that gets or outputs the time to the guest operating system. So, of course, this emulation, in order to emulate the whole peripheral device, its registers, how it behaves, it's very costly. The good thing is it is hardware independent, but of course it's extremely slow, as we will see. Next, for paravirtualization, we see that this approach tries to do things differently. Instead of emulating devices, it tries to make the guest operating system aware that it is running under a hypervisor. In essence, that means that instead of emulating a storage device, for example, the driver of the operating system knows that it's a virtual machine. So no need to emulate a storage device, but instead we will use a disk file in the host system, and that's it. The advantage is that it's relatively fast, but the major disadvantage is that we need to modify the guest software, and sometimes this is not an option. So paravirtualization cannot cover everything. Finally, we have hardware-assisted virtualization, among the most efficient ways to virtualize things, but also the most costly in terms of hardware. So newer platforms, newer hardware comes with specific virtualization extensions that help the programmer implement a hypervisor to efficiently schedule resources and manage them, and virtualize them, of course. Various examples for this, for the Intel and ARM architectures, where we have CPU and memory virtualization. This is hardware support, of course. So the software runs in conjunction with these extensions, and if the hardware does not support, you cannot be as efficient. The advantage is that you get near-native performance, but the major disadvantage is that not all hardware supports these extensions, and some architectures do not even come with them. So this is finishes the small presentation and the introduction to the virtualization concepts. Thank you for your attention.